In the previous video, we had learned about the introduction to Boyle's law. In this video, we are going to be talking about the graphical representation as well as the experimental observations. So before we start, the previous video we had learned that pressure is inversely proportional to volume. That's the first equation. So pressure, and this is at constant temperature and a fixed amount of gas. So P equals to K1 into 1 by V. We had also learned about the variation of volume and pressure as P1 into V1 equals to P2 into V2. So P1 by P2 equals to V1, V2 by V1. So for a clearer understanding about these equations, do check out that video. But these are the equations that we had learned. First graph over here is between the pressure and the volume at obviously constant temperature and the fixed amount of gas. So when a curve is drawn, okay, and we are extrapolating 2 points, okay, and we are observing the volume as well as the pressure in each case. So from here, it's actually, so before we start, at a pressure P1, the volume of the gas is V1, and pressure P2, the volume of the gas changes from V1 to V2. So from here, it is actually pretty obvious that V1 is lesser than V2 and P1 is greater than P2. So V1 is less than V2, P1 is greater than P2. So when there is an increase in, or rather when there is an decrease in pressure, the volume is increasing because pressure and volume are inversely proportional to each other. So here when pressure was P, it's high, right? So at that time the volume was low. But when pressure was decreased, then the volume changed from V1 to V2, which means the volume has increased. And this graph shows that pressure and volume are inversely proportional to each other. Now in this graph, that's the second one, we have three curves. We've just had one curve, and so we assume, this is at a particular temperature and fixed amount of gas. But this case, you have three curves. Okay, and each of them corresponds to a particular temperature. So this is at 200 Kelvin, this is at 400, and this is at 600 Kelvin. So these three have a variation in terms of temperature, but the number of moles or the amount of gas is fixed. So there is no change in the amount of gas, but there is only a variation in terms of temperature. And because one of the constant values is actually changing in each case, you have a variation in the K1 value. So K1 for this curve will be different from K1 for this one. It will be different for this one. So the value of K1 is not going to be the same in all the three curves. That is the first thing I would like to say. The second one is that these curves are actually called as isotherms. Okay, these the curve which is present at a particular temperature, which is it's corresponding to a particular temperature, is referred to as an isotherm. The next one, this graph, is between pressure and 1 by volume. And notice, because we took here we just took volume, right? And the graph or the straight line, the curves which were obtained did not pass the origin. But in this case, 1 by V, when we're taking 1 by V, we have a graph where the lines which are obtained are passing through the origin. That is the first point. Obviously, the temperature is constant for a particular line. So in each case, you're going to have a fixed amount of gas. And not only that, in this case also, T3 will be greater than T2 will be greater than T1. So when we're drawing a graph between pressure and 1 by volume, it should be decimeter to the power -3 because it is 1 by volume. Remember, you need to put the units of the quantities that you're having on the x and y axis. But here So here and here you have, when pressure and volume are taken into consideration, we got curved lines. Whereas when we took pressure and 1 by volume, we got straight lines passing through the origin. And each line is for a particular temperature. And notice that T3 is higher than T2, which is higher than T1. At higher pressures, gases actually deviate from Boyle's law. So in those cases, we do not get such a straight line, which is observed in certain cases. Now, the last graph that we have over here has PV on the y-axis and P, that is the pressure, on the x-axis. Now, we learned that P into V. Remember, when I said PV equals to K1, so the product of pressure and volume at a constant temperature and number of or fixed amount of gas is going to stay constant. So here PV, the product of pressure and volume versus the pressure, when we basically plot the graph, we notice that we get straight lines. And obviously when there is a change in temperature, the line's position is at a different place, but even then we are just getting a straight line, and that is because of this equation. Okay, pressure and the product of pressure and volume when the temperature and the fixed amount of gas, then the product is constant. So this is actually a proof or a graphical representation of that particular thing. So PV remains constant even if pressure is changed. So here we'll have a value P1, here it will be P2, P3, P4 or P5, right? But no matter what the value of pressure is, the value of PV is a constant. The next, so, and similar to these graphs, higher value implies higher temperature. So T2 is greater than T1. With that, we have finished the graphical representation. The first graph, it's a basic graph of Boyle's law. Pressure is inversely proportional to volume. So when pressure is low, volume is high. When the pressure is high, volume is obviously going to become low. The second graph is basically the variation of pressure and volume at various temperatures with a fixed amount of gas. So here you have 600 Kelvin, 400 Kelvin and 200 Kelvin, and obviously this is also following the Boyle's law. The third graph is between pressure and 1 by volume. So see, here when pressure is increased, 1 by V is also increasing because pressure and volume are inversely proportional to each other, and these lines are obtained where they are going to meet the origin. Oh, one more important thing, the value of K1 is going to vary for each and every temperature line over here. The last one is PV versus P. We know that PV is equal to K1. So P, the product of pressure and volume, is a constant at constant temperature and fixed amount of gas. So PV, no matter what the value of P is, the value of PV stays the same. And this graph actually shows that because the value, you're getting a straight line. Next, let's just see the variation of, here we have the experimental data of the effect of pressure on volume of 0.09 mole carbon dioxide gas at 300 Kelvin. So here we have the fixed amount of gas, that is 0.09 mole, and the temperature is also fixed at 300 Kelvin. Now, instead of trying to tell you, okay, see, when we increasing the pressure, the volume is decreasing, so it follows the Boyle's law, which is correct. But let's look at it from these perspectives. Okay, so here you have 2.0 and 112. So obviously when the pressure is going to be low, the volume is actually pretty high, and that is actually clear from this graph. So similarly, if we talk about 10, okay, 10.0, the volume is 22.4. So I'll assume that 10 is over here, then the volume is actually the least in that case, so compared to all the other values. The next one is the relation between P and 1 by V. So when it's 2, it is at 8, and then you have it at 11. So it's increasing. Both of them are increasing. So 2.5 is 11, 3.5 is 15, 4.0 is 17.7. So with the increase in p value, there is also an increase in 1 by v value. The last one, if you notice, when I remember I told you that when you take the product of p and v, it's going to stay constant. So if you notice over here, they're all quite close to each other. They're all 22, but like after the decimal point, you have 22.40, 22.30, 22.47. So all of these are quite close together. And when we plot a graph between the pressure and the PV, product of pressure and volume, we will actually get a straight line. And these values will make sure that, I mean, you might get it as close as this. So it might be like so, but even then, these values are very close, and because of that, we will get a straight line. So we can see that the experimental data which is obtained actually follows the Boyle's law. So with that, we're done with the graphical representation as well as the experimental verification of Boyle's law. In the next video, we will be talking about the practical significance of Boyle's law. So do check it out.